Hello. Today we would like to expand about element of communication system, impedance matching network. What is impedance matching network? It connects one stage that with to another are very important of a part of the transistor. This circuit will be used to connect from one stage to another stage, which known as impedance matching network. And typical network we have LC circuit, transformer, and some combinations. Impedance matching networks, the main function is to provide an optimum transfer power through the impedance matching technique and also provide the filter and selectivity. And we can see here we have the circuit of the impedance matching network in RF circuit. Here we have RF generator. This part is the RF generator. Okay. Inside this RF generator, we have ZI indicate the internal source of impedance. And we have at the right side is the load ZL, impedance for the load. Okay, so in between this line, we will add the impedance matching network. This impedance matching network can be formed by a capacitor or inductor and etc. Okay, we have three basic type of the LC impedance matching network. They are L network, T network, and pi network. Okay, L network consists of an inductor and capacitor in a L-shaped configuration. It used as a low or high pass network. Low pass are preferred because the harmonic frequency are filtered out. And the L impedance matching network is designed so that the loads of the impedance matching is matched with the source of the impedance, which means the ZL is equal to the ZI. Okay. So we can see here, this one is our inputs internal source of impedance. So we have ZI equals to RI. Okay. And here is our L network. So it formed by the L and the C, inductor and capacitor, then connect to our load. So our load will have ZL. So for the L type, we have two types. One is it will connect series with the L and parallel with the C. And this one known as the Z have the condition ZL is smaller than Z in. Okay. So we are using the formula XL equals to integrate R in R L minus of RL square. So R here actually is indicate the Z. So which because of the Z the impedance for the loads is smaller, so that's why we minus off the RZ or RL or ZL. So minus off the impedance of the load. So we also calculate the Q. Q is the quality. So we will have Q equals to integrate R input divided by R load, which means is our input source impedance divided by our load impedance, and then minus 1. Okay, then we can from here, we can calculate our XC, our capacitance, equals to our impedance of input multiplied with our impedance for the load divided by our inductance. Okay, so we must fulfill these conditions. Okay, the second type of the L networks are here. So we can see the Z input, the input source is equal to R in. Okay, so this one is our load. Okay, the difference for the second type is here. It series in L and then parallel in capacitor. But start with L first, then connect to capacitor. So this is the difference. Okay, one, the capacitor is come first, then only this one is a type 1. Okay, type 1, the first type, and then this one is second type, type 2. And for this type 2, start with inductor, then go to capacitor. So we know that in this case, the loads, the impedance and the loads will be bigger than the input impedance. So we can calculate our XL equals to square root of our input, then our loads minus of our impedance of the input square. And then we can calculate our Q. Q is a quality, equals to square root of our input divided by our load impedance minus 1. XC is equals to our R1 RL divided by our inductance. So in this case, we must fulfill this rule. Only we can use this formula. Now we go for example. Calculate the value of the capacitor and the inductor of our L network, impedance matching network. By given a 6 ohm transistor amplifier, impedance to a 50 ohm antenna load. Okay, at frequency 155 megahertz. So from here, we have to refer back our L network, and we can see this one is the input Z in ZI is 6 ohm. So from here, and the ZL is, the load is 50 ohm. And we have the frequency F is equal to 155 megahertz. First step, we have to refer back our L network. So for this case, we know that our ZL is bigger than our ZI. So we have to using type 2 circuits. Type 2, this one is the type 2 L network. Okay, we are using this type 2 L network. So start with L because we have to fulfill these conditions. So we have to use this formula XL, Q, and XC, and have to minus off our our I because I is smaller. Okay, so first step we find our XL by using this formula. Okay, and our XC as well. So we are putting into the formula XL equals to square root of RL minus RL square, RI square, I square. So equals to 6 multiply 50 minus 6 square. So we have 30, 300 minus of 36. So we have square root of 264, which means equal to 16.25 ohm. Okay, then we're using the next formula Q, square root of RL divided by RI. minus 1. So 50 divided by 6 minus 1, we get 2.7. Okay. Then we can find our XC by using the formula RL, RI divided by XL. 50 multiplied by 6 divided by the XL that we calculate previously. Okay, from here. Okay, 16.25 ohm. Okay, divided by 16.25. So we obtain 18.46 ohm. So now we get the value of Xc, our capacitance and inductance. So we can find our inductor value and capacitor value at the frequency of 155 megahertz. So we using XL equals to 2 pi FL. So we rearrange the formula. So we get L equals to the impedance of inductor. Sorry, it's not the impedance. It's the reactance of the inductor, XL, divided by 2 pi F. So equals to 16.25 divided by 2 pi F. We will have 2 pi will have 6.28 multiplied with 155. Our frequency power of 6 is a mega. Okay, equals to 16.7 nano Henry NH. Then we can find our capacitance, okay, equals to 1 divided by 2 pi Fc. So we have C equals to 1 divided by 2 pi Fx and equal to 1 divided by 2 pi is 6.28. Our frequency 155 times 10 power of 6 and multiplied with our capacitance 18.46 equals to 55.65 picofarad PF. So we obtain our answer. That's it. Easy. Done. So now we go to the next network. So we now go to T and pi network. Okay, this T and pi network is better to control the Q or the selectivity of the circuit. The impedance network using 3 reactive elements. Okay, that's why it have the shape of pi or T. Okay, the pi network is designed by using the reactive element in the configurates that assemble the grid letter of pi. Okay, for the T network, we were using the reactive element in the shape of T letter. So now we go for our figure. Okay, so this one is a pi network. So we can see it have the shape of pi. Okay, so this is 3, 1, 2, 3 reactive element. Okay, now we go to T network. So we have a shape of T. Okay, same, we have 3 reactive elements. 1, 2, and 3. Okay. Okay. Now we go to the example of T networks. Okay. How we want to design a T networks? So to design a T networks, okay, we have the inputs and we have the outputs. When we want to design a T network, we want to know the value of L, inductor, capacitor, number 2, and capacitor 1. So for this T network, we know that we must fulfill our rules that our input impedance must be smaller than our output loads, our impedance at the loads. So to design the process, first we must select a desired circuit of Q. So we have to determine our quality of the circuit Q or depend on the questions that given. Okay, second, we want to calculate the XL. So our inductance equals to Q multiplied with our R in. Okay, this one. Okay. Then step number 3, okay, we find our XC, the first one, C1. Okay, to find our C1, to find C2 first. Sorry, here is C2. To find our C2, XC2 equals to RL. You see our loads, impedance at the loads in, and we have this one, square root of R in, okay, Q multiplied with Q2 plus 1 and divided by RL minus 1. Okay, then we also calculate for our XC1. Okay, we have R in multiply with Q square minus plus 1 divided by our Q and multiply with 1 over 1 minus XC2 divided by QRL. Okay, we will get our capacitance for the C1. Then after that, we compute the value of L using the formula L equals to XL divided by 2 pi F, and C, our capacitor value is 1 divided by 2 pi F XC. That's all. It's very simple. Okay. Now we go to the example of T-network. Design a T-network circuit with a 6 ohm source of Rin, Ri, okay, is to be matched to the 50 ohm load RL, okay, at 155 megahertz, given Q is 10. So from here we have first information is R1 equals to 6. Second information we have RL is equals to 50. The information we have frequency equals to 155 megahertz and Q equals to 10. Okay, we list down these 4 information. We start the first step. Okay, now we list down. Okay, start with first step. Find the inductor. Okay, we're using the formula XL equals to QR in. So we calculate XL equals to 10 times 6, we get 60 ohm. Okay, then we find our L equals to XL divided by 2 pi F. So 50 divided by 2 pi, 6.28 times 155 times power of 6. 10 power of 6, so equals to 51.4 nano Henry. Next, we continue with second step to find the C2 capacitor. Okay, so C2 equals to the formula 50. Okay, so we can refer back the formula. Okay, this formula. Okay, this one. Okay, RL is 50, R in 6, Q is 10 square plus 1 divided by RL 50 minus 1. Okay, so we see here. Okay, 50. So here 6. Then we have 101. Okay, divided by 50 and minus 1. So now we have 50 multiplied with 3.33. So we get 166.73 ohm. Then we have C2 equals to 1 divided by 2 pi Fxc. So 1 divided by 6.28 times 155 times 10 power of 6 times 166.73, and we will get 6.16 picofarad. Then we go to step number 3. We find for the C1. Same also, to calculate this one, we using the formula here. Okay, we're using this formula. Okay, R in you have 6, then Q you have 10 power of 2, 100 plus 1, so you have 101 divided by Q10, and then here you multiply with 1 divided by C2, so you calculate just now. Okay, then divide by Q 10 and R L 50. 10 minus 5 50, then you have 500. So you can see here. Okay, see 10 multiplied by 50. Okay, here same, you just fill in the value, so you'll get 60.6 times 1.5, so equals to 91 ohm. Okay, then to calculate our C, so 1 divided by 2 pi f xc, so 1 divided by 6.28 times 10, 155, 10 power of 6 times with 91, then we'll get 11.3 picofarad. Okay, simple. Now we go to transformer and balloon. Other than this T network, L network, and pi network, actually this impedance matching network also can be used as the transformer or balloon. One of the best impedance matching component is the transformer. So we have the first is ion cord transformer are widely used at the low frequency to match the impedance. Any load's impedance can be made to look like the desired loads by selecting the correct value of the transformer tune ratio. Okay, transformer used to connect and balance source to the unbalanced loads and vice versa. That's why we known it as balun. And this balance is come from balance dash unbalance. And combine these two words become B-A-L-U-N, balun. Okay, then we have also another one is A core transformer is widely used for RF and is less efficient than the ion cord transformer. And we also have another type is a single wing tap coil called as auto transformer, are also used as the impedance matching network at the RF stage. And we also have another one which is widely used named toroid, and toroid is a circle or donut shaped coil, okay, usually made by a special type of the powered iron. Okay, now we go to thyroid. So this thyroid transformer is cause the magnetic field. It will produce the magnetic field, and by the primary to be completely attend with itself. And it has two advantage. The first advantage is it does not radiate the RF energy. Second advantage is most of the magnetic field produced by the primary, it will cut the turn of the secondary wing. So the basic ratio and the input voltage and the impedance matching network for the lower frequency transformer is able to apply the frequency, the high frequency of the thyroid transformer. Okay, due to this advantage. Okay, so this is the circuit of the diagram of the thyroid transformer. So we have the primary coil, then connect to a powered loads thyroid and to secondary coil. Okay. Then we also another type is transmission line transformer, and this transmission line transformer is a broadband transformer. Okay, and it widely used in the power amplifier for coupling between the stage and the impedance. So it constructed by two parallel wire or a twisted pair on a thyroid. Okay, this is the figure look like. Okay, they have two pair of thyroid, 1 and 2, and this 2A and B actually is the coil that rotates in the power cords of this iron. Okay, Now I give some example on this ion coil transformer. Okay, ion coil transformer is look like this. We have RF generator. Okay, this one is our inputs. And then we have the primary, then we connect to our secondary coil, and then this secondary coil will connect to with our impedance of the loads. This load will connect to the antenna. Okay, this one is the antenna, load of the antenna. Okay, okay. So to calculate the ratio, between these two turns. We have the n primary. Here is the number of your primary turn, and n for number of your coil of the secondary turn. So to calculate the ratio, turn ratio, we will equal to np divided by ns. Okay, the relationship between the ratio turn and the input and output impedance is here. So for the input impedance, Z in Zi divided by Zl loads equals to, okay, bracket our number of primary divided by number of coil for secondary, okay, square. Okay, so we can okay, so if to rearrange the equation, so the NP, the number of primary divided by number of coil for secondary, will equal to square root of impedance of the I and Z loads. Okay, so here have a questions. Find the turn ratio to match the generator impedance of 6 ohm to 50 ohm loads impedance. So how you want to do? So we just use the formula just now. The number of the primary coil, okay, divided by the secondary coil, okay, equal to our square root of Zi divided by Zl, okay, equals to square root of 6 divided by 50. So square root of 0.12, so we get 0.3464. Okay, so for the ratio ns, our secondary to the primary, so we will have 1 divided over our np divided by ns, so we have 1 divided by 0.3464, so we will get 2.887. Okay, this one is our turn ratio value. Okay, thank you. Remember to subscribe my channel below here and like and share. Bye.